So firstly, let's talk about discrete probability distributions. So a probability distribution is where you've got an event which has a number of possible outcomes, and you in some way describe the probability of those outcomes. If it's discrete, that's not the discrete as in, it's all sort of private, and it's discrete as in discrete data, which is data that can only take certain values. And so, one of the most basic questions we meet with probability distributions are tables like this, where you've got a number of possible values and then the probability of those values. I saw a question the other day that said the probability of cloud cover can be described with a uniform distribution on a particular day. So that's a reference to the large data set. Can anyone tell me how cloud cover is measured in the large data set? Octaves, that's right, it's eighths. How much of the sky is covered in terms of how many eighths? So in that case, you had the possible results 0, 1, 2, 3, 4, 5, 6, 7, and 8. Now, cloud cover clearly is not normally a uniform distribution, but if in this question it was on this particular day, what that meant was all of these probabilities would be the same. I've got 9 different values, so they would all be 1/9. So this is an example of a discrete probability distribution, but it's also a special case, a uniform probability distribution. Remember, we also get those questions where the probabilities aren't described in a table, but they're described with a function. It will say the probability of 0, 1, 2, and 3 is this, and the probability of 4, 5, and 6 is something quite different. And we have a special case of discrete probability distribution. So I say, okay, we've met 2 special cases. This is a uniform probability distribution, but the case that we need to be most confident with is a binomial probability distribution. And the binomial probability distribution is a special case where you're doing something a fixed number of times. And every time you do it, there's a fixed probability of success. And the result of one event doesn't affect the other event. And those events can be described with success or fail criteria. So those, I'm not going to write those down, we've got those written down many times, but those are the 4 conditions for a random variable to be described using the binomial. And we describe the binomial with the number of times it happens and the probability that that thing happens. So probability distributions are just a description of the probability of a number of different events. A uniform one is where all the probabilities are the same. The binomial is a special case where we are doing something a repeated number of times, and each time we do it, this is the probability of success. Right. Okay. So let's just check that this situation is one where the binomial is relevant. Are we doing something a fixed number of times? Yes. Every time we do it, do we have a fixed probability? Yes. Have we got success-fail criteria? Well, yes. We're basically categorizing it as hits the bullseye, doesn't hit the bullseye. Does one event affect the other? Well, this is probably where the model breaks down, because I would argue that, particularly if you're outside, it's a bit windy, one arrow is probably going to affect the way you shoot the next arrow. But when we use the binomial, we have to assume that one event is independent. So I'm hoping that for part A, you're going to be able to put your calculator into stats mode and tell me that probability. let's call x the number of bullseyes that she hits, okay? And you've just got to be really careful with the wording, at least. Just be there. Has everyone got calculation books there? So for those at home, this is the other group, page 97 in the Stats 1 textbook, question 15. Page 97 in the Stats 1 textbook, question 15. So I'm sort of hoping we're on autopilot, but we go to statistics, we go to dist for distribution, we choose binomial, and we choose BCD for binomial cumulative distribution. Excellent. We make sure it says data variable, and I always like to have it, it's not symmetrical automatically, but I always like to do a little sketch. At least half of them means that, doesn't it? Remember, it's not symmetrical, so although with the normal distribution this would be a half, with the binomial, not necessarily. So I'm going to put my lower is 10 and my upper is 20. Remember, 0 is a possible score if we were doing less than 10. And we tend to go to 4 decimal places because that's the way the old-fashioned tables go. Now, the reason I chose this question is part B, because you know those Russian dolls. They probably won't be called Russian dolls much longer, will they? They'll be called Eastern European dolls, where you open one doll up and there's another doll inside it. Well, we've got a similar sort of thing here. We've got a binomial problem here within a binomial problem, because shooting 20 arrows is like one go. And in part B, she does that 12 times. So in part B, we're talking about something that she's doing 12 times. In part A, the thing was shooting an arrow, and she did it 20 times. In part B, the thing she's doing is shooting 20 arrows. Now, in part B, success is that she hits the bullseye with at least half of her arrows. What's the probability of success? That's the answer from the previous question. And we're asked, what's the probability that she does that 7 times? Just 7. Although it's just 7, remember we still use BCD, we still use binomial cumulative distribution.
I've got toilet pass. I know, I've literally just seen it when it was a 6 on my bike. I've got toilet pass in.
So please do that.
We're not going to do part C, but I'm sure we could. So you have to change all your values, don't you? So we're now talking about 12 trials. The probability of success, 8725, which is an estimate. It's not an exact value, but we're modelling, so it's it's okay. And this time I just put my lower and upper of both as 7. And frustratingly, they go to 4 significant figures. Does it say in the answer? No. So 4 decimal places is plenty. 4 decimal places is plenty. So that's the binomial. That's the binomial. So we're now going to jump to Stats Book 2 and page 94. Stats Book 2 and page 94. That's not page 94. Page 44. Page 44, sorry. My writing. And question. So now, in this case, we are now dealing with a probability associated with not discrete data, but continuous data. So we're now talking about a continuous probability distribution. So we're no longer working with the binomial, which is discrete. We're now working with a continuous probability distribution. And in this case, the thing we are measuring is the amount of mineral water in a bottle. And what we find is that in most cases, if you measure lots of continuous things like this, unless there's something amiss, the data tends to be normally distributed. Most of the capacities will be in the middle here. You'll have a few low ones and a few high ones. And we describe this using the mean and standard deviation. And we know that there's a predictability. We know most of our values will be within 3 standard deviations of the mean. And we can work out probabilities using this. So continuous probability distributions, there are a number, but the only one we meet is the normal probability distribution. And so in this case, we're saying the capacity of water in each of these bottles is normally distributed, and in some way they've calculated that on average they're getting 500 millilitres in each bottle. And the standard deviation is 14. And if you remember, rather frustratingly, we actually use the variance, the standard deviation squared, in the description. So now we need to flip our calculator into normal distribution mode. Let me show you the answers and see if you can get those answers on your calculator. It's a little bit more complicated when you come to a greater than, isn't it? It's a bit more complicated when you come to a greater than. Statistics, distribution, normal, NCD. And frustratingly as well, they, on that table, they put the standard deviation first before the mean. So for this one, we've got a lower of 505, but what we don't know is the upper, because with the binomial, that's fixed. You're doing it a certain number of times. But with the normal, well, you know, we don't know what the biggest possible is. So we've got a couple of things we need to consider. The vast majority of the data is within 3 standard deviations of the mean. So we would need to say, right, I need to at least go 500 plus 3 lots of 14. But actually, there's nothing wrong with just whacking in a big number. So I did 505 as my lower, 700 as my upper. But if you put 4 million as your upper, it's not going to change your answer. You're going to get that answer. So don't worry about your upper being, you know, exactly 3 standard deviations and feeling you've got to show that method. No need, no need. Just put a big number in. For the second one, it's 0 as the lower, 490 as the upper. Now I know this is saying what's probability it's less than 490, but this is continuous data. So we're not saying it can only be 489 or 490 or 491. So we put 490 in, because actually less than 490 is 489.9 recurring, isn't it? So we put 0 to 490, although I suspect if you put 0 to 489, you probably would get a value that rounded to the same, but we don't. We use those actual values. Now, can you see why I chose this example? Because what happens is we now do something 4 times. We take a sample of 4 bottles. So we're back to the binomial. So we're back to the binomial now. So we are now dealing with how many bottles have more than 490 millilitres. So it might be that we have none of them. It might be we have 1 of them, 2 of them, 3 of them, or all 4 of them. So we're back to a binomial scenario. So we're now saying in my sample the number of bottles which are more than 490 is this. Now hang on a minute, I don't know the probability of more than 490. I know less than 490, so it's 1 minus that. Although of course we don't actually need to do that. We could do a bit of a shortcut here, but just bear with me. So I'm going to do I'm going to do 1 minus that to get my probability. And I could use my calculator, the binomial, to do that. I'm wondering if you might feel that you can do it a second way. And if you can I get you to try both ways? One is using the calculator to work out the probability of just 4. See if you can think of another way and then compare the 2 answers. All right? See. So hopefully you were able to get that with your calculator. Could anyone suggest how we could do it without the calculator? How could you do it, George, without the calculator? The probability that all of the bottles contain more than...
Really good guess.
Well, it's the probability that the first one does, and the second one does, and the third one does, and the fourth one does.
Oh.
So you could just have done that for para 4. Now, the only reason we can do that with this, and we can't do it normally, is that there's only one way this could happen. The complication with the binomial is if it was 3 that were more, then you could have the first 3, the first one, and the last 2. Yeah, there's several ways it could happen, which is why the calculator speeds things up for us. But with that one, you could have got the same answer either way. Okay, so this was a normal distribution where we were told mean and standard deviation. Do you remember that we did come across questions where we had to work out the mean or the standard deviation? Here is an example. I'll give you a chance just to read that. So this is 2019. I don't know what paper did it say? 29. Oh, it's only one stats paper, isn't there? So yeah, so it's 2019 from the stats paper. So we're told that the amount of liquid in each bottle follows a normal distribution. So they're calling that D, and we're told the mean is 25. But we don't know the standard deviation. But we need the standard deviation in order to answer an inverse question like this one. So we've got to work out the standard deviation. So this is the probability distribution for this one. And we're told that 15% of the bottles contain less than 24.63. So I've drawn that information on my picture, and I always think with both binomial and normal, a sketch is really, really helpful, particularly with hypothesis testing, although that's not the focus of today. So what we do with these missing value problems is we say, well, actually, let's pretend we're dealing with a standard normal distribution. So this, I'll use X. This is a normal distribution with a mean of 0 and a standard deviation of 1. And let's work out what this value here is that gives us a probability of 0.15. So let's work out that value there. So we need to go to inverse normal, and if you remember, that gives you the option of left or right tail. And we need to tell it that we're looking for, well, it's a left tail problem, and we're looking for the value that gives us a probability of 0.15. See if you can remember that. So that's stats, dist, normal, inv, or inven, I think it says, isn't it? And what we do is we enter 0 and 1 as our standard deviation and mean, remembering, well, sorry, 1 and 0, remembering if they want the standard deviation first. And what that tells me is that in order to get a probability of 15%, or 0.15, you need to go 1.0364 standard deviations below the mean. That's what that's telling us. When we use this standard normal distribution, that's what the answers tell us. So I now know that this is 1.0364 standard deviations below the mean, 25. So I know that 24.63 is the mean minus 1.0364 standard deviations, and I want to know the standard deviation. When I've done this, for some reason I've rounded mine to 3 sig figures, but which would be perfectly acceptable. I'm hoping I'll get something similar to that. So I've used this concept of a normal standard distribution where the x values it gives me are how many standard deviations above or below the mean I am, to work out the standard deviation. I could have done the same if I'd known the standard deviation to work out the mean. It just would have been a similar sort of sum. What are we actually asked in part A? Find the probability, find the value k such that the probability of 24.63 up to k is 0.45. Now the good news is that I can go back into and re-enter my variable. Now I've actually got a full figure. I don't need to work with the normal standard normal distribution anymore. But what I'm interested to know is how you're going to do that question. What are you actually going to type in? You need to use the inverse function. I'll give you that much. So I did it by doing a left tail and asking what value gave me a probability of 0.6. because it was the 0.15 and the 0.45 that was after, and I got 25.0904. We can have a look at the mark scheme just to confirm what it says about accuracy. Answer which rounds to, that's what that means. So anything which rounds to that is okay. Right, now, the second part of this question actually is about hypothesis testing, another lesson. So we're not going to do that now, but we are going to do one more question. Okay, so this is the last bit that we need to cover in terms of the normal distribution. And this is particularly important because the pre-release says discrete probability distributions, doesn't explicitly mention binomial, but then says the normal approximation. And one thing you can do is use the normal to approximate an answer to a binomial problem. So that's going to be a question just like this. It then goes on and says normal distribution as well. So I think there'll be two normal distribution questions on there. One where it's mixed in with a binomial and one where it's on its own. Unless that's them describing one question. I don't know. So this part A is a normal binomial question. Okay? So X is the number of boxes that contain a prize. And someone has bought 100 boxes. They must really want a prize. So see if you can use the binomial to answer part A. Okay, so I'm being lazy. Hopefully you got that. Now, one thing you can do, and you can only do it in certain situations, is you can use the binomial to approximate the value of you can use the normal to approximate the value of a binomial probability. Now, why bother doing that? Well, this is a historical thing. It was quicker to work out normal probabilities than binomial probabilities before these calculators came along. Now, there's no advantage. But we can only do that if two things are in place. One, the binomial probability distribution is not automatically symmetrical. For example, my regular thing, me and James played 7 games of tennis. He's much better at tennis than me, so the probability of the number of games he's going to win, it's going to be skewed like that, isn't it? That's going to be the probabilities. You only get symmetrical binomial probabilities if the probability is a half. With normal distributed data, it's always symmetrical. So the first thing we need is we need a probability that's close to a half. The other thing we need is a lot of trials, because the approximation gets better as we do more and more. So we always say n needs to be large. And that's deliciously vague, isn't it? But we've got 100 here, so we'll say 100 is large. So what we do is we turn our binomial parameters into normal parameters. We need a mean and we need a variance. And at this point we reach for our formula books in case we've forgotten. I'm going to put mine up on the board so you can, if you haven't got yours. And on page 8. On page 8 we see We see this little table here that says if you've got a binomial and you want to know its mean, you do n times p. N times p. I always say this is just what do you expect to get. If you do something 100 times, every time your probability of success is 0.56, you're going to expect it to happen 56 times. So that is n times p. The variance, which remember is the squared, is the standard deviation squared, is n times p times 1 minus p. So in this case, it's going to be 100 times 0.56 times 0.44. And that's the variance, so the standard deviation will be the square root of that. But I think your calculator lets you type in a sum in that box. If it doesn't, you might have to work it out and enter it in. And do you remember the final tweak that we need to make? Because 55 is from a discrete distribution, and we're trying to squeeze it into a continuous distribution, we have to use the values that would round to 55, the error interval of 55. So when we come to use our normal distribution on a calculator, we actually need to do 54.5 to 55.5. The range of values that are rounded to 55. So will it let me type? So, and this is we're not in inverse. We need to go back to normal cumulative distribution. Does it let me type in the square root? Oh yes, it does let me type in. So remember, this value from the formula book gives us the variance, which is what we always put there, but in our calculator we need the standard deviation, so it's the square root of that. But it allowed me to type that in. I wasn't sure whether the square root's going to stretch across, so I put it all in a bracket, because it did this sort of funny, it did that, so I just put that in a bracket. And these are often percentage error questions, so I'm going to do the if after divided by before, so my before is my actual answer, so that's the binomial. So I'm going to do this, and I'm going to use the rounded values because that's all I've got. I'm hoping it'll be accurate enough. Not accurate enough, right? So I should have saved my more accurate answer. So that's if I typed that in over a more accurate version of the original one, hopefully you would get, I'm only getting 0.26% rather than 0.31%. But it's the incorrect one, the normal one, over the original, and that gives you the multiplier. What I might do is I didn't save it, I might go to the solution panel just so we've got the actual numbers. they've done it slightly differently. They've done the change over the original, but there we go. I do it. I get 1.00 whatever. So you take the exact value of that, or as much as you can type in, over the original value, which I never worked out, so I didn't have it stored, and then multiply by 100. Not an exam question, so I'm sure in an exam they would be more forgiving in terms of the range of values they would accept. But the normal approximation to the binomial is explicitly, there aren't many things that are explicitly mentioned. This is explicitly mentioned. So remember, it only can be done when n is large and when p is close to 0.5. So if it says what are the conditions, that's it. We need to work out our mean and variance, and we also need our little tweaks for our values to make continuous into discrete. Look at that, it's not often that I finish and do exactly what I want. We have a couple of minutes left.